This video is going to focus on inductive reasoning. And the examples are going to try to answer the essential questions: what is inductive reasoning, and how is it used to make and test conjectures? Inductive reasoning has to do with patterns, and so the first example here is to describe a visual pattern and to extend it to sketching an additional figure, the fourth figure. So here's figure 1, it looks like a circle cut in half. Figure 2, a circle cut in fourths. Now it looks, by appearance, it looks like each time we are cutting the figure in half, and so far that's what we've been doing, but this third figure is not cutting the area in the second figure in half. Instead, it's just adding one more diameter to the circle. So you can see here we have a circle with one diameter, namely this line here. Here we've got a circle with two diameters, these two here. Here we've got a circle with three diameters, 1, 2, 3. And so in anticipating the fourth figure, we can anticipate a fourth diameter. And back up. The figure should look like this. You can count four diameters. Okay, we can do the same thing in describing a number pattern and then extending the pattern to what we think might be the following numbers in the pattern. Here's an example. Can we figure out what's going on in the sequence of numbers? Well, to get from -7 to -21, we need to multiply by 3. From -21 to -63, we're going to multiply by 3. -63 to -189. So each time it looks like our pattern is multiplying by 3. How are we going to get the next three numbers in the pattern? We'll take -189, multiply that times 3, and that should get us -567, multiply that times 3, -1701, and the last number there is multiplied by 3 to get us -5103. Making a conjecture actually is taking a pattern and then coming up with some type of a rule or a formula for what's going to happen at any point in the future if the pattern continues. So here's an example. Give 5 collinear points. We're going to make a conjecture about the number of ways of connecting pairs of points. So let's look at the pattern here. One point cannot be connected at all. If we have 2 collinear points, we see just one connection between the two of them. 3 collinear points, the first point can be connected to the second and to the third, so 2 connections there. The second and third can be connected for a grand total of 3 connections. Let's observe 4 collinear points. If we just concentrate on the first point, we can connect it to the second, to the third, and to the fourth, so there's 3 connections. The second point can be connected to the third and to the fourth for 2 more, and then we still connect the third and the fourth, and that gives us a grand total of 6 connections. So now, at this point, we've got enough of a pattern to analyze what we might think 5 collinear, how many ways there might be to connect pairs of points collinear. We can see here that each time we are increasing the number of connections by 1. Here we're increasing the number of connections by 2. Here we're increasing the number of connections by 3. We can anticipate increasing the number of connections in this next one by 4. We can anticipate there being 10 connections there. Okay, so let's see what that actually looks like. Here are 5 collinear points. The first point connects to the other 4, the second connects to the remaining 3, the third connects to the remaining 2, and of course the last 2 connect for a total of 10, just as we suspected. Finding a counterexample, we need to come up with a counterexample to disprove the following. The conjecture, the sum of 2 numbers is always greater than the larger number. Well, that's true if the 2 numbers are positive, but we can come up with a counterexample where the one of the 2 numbers at least is a negative number, and that one counterexample disproves the conjecture.